Today we are going to talk about the regulation of the glycolysis. Here in the today's chapter we will talk about how glycolysis is regulated by the different steps and different enzymes, how the substrate or the products regulate the glycolysis. Now let us start this topic. The three steps catalyzed by the enzyme, mainly hexokinase or glucokinase, phosphofructokinase and pyruvate kinase. You have to know that these three reactions which are catalyzed by these enzymes hexokinase or glucokinase, phosphofructokinase and pyruvate kinase are irreversible. So these irreversible steps mainly regulate the glycolysis. Again, I am going to tell this. Most of the reactions of the glycolysis are reversible. However, the three steps catalyzed by the enzyme hexokinase or glucokinase, phosphofructokinase and pyruvate kinase are irreversible. These three steps mainly regulate the glycolysis. So you have to know this. You have to know that mainly the irreversible steps regulate the glycolysis. If you don't know the various steps of glycolysis and you are still confused about the glycolysis step, I request you to know those steps and I request you to write down the detailed steps of glycolysis in your note and see this video side by side so that it will be clear to understand the regulation of the glycolysis. Now let us discuss the actual regulation of the glycolysis. As I have already said, the three enzymes, namely hexokinase, fructokinase, phosphofructokinase and pyruvate kinase, catalyzing the irreversible reaction, regulate the glycolysis. First of all, let us talk about the hexokinase. In the glycolysis step, the hexokinase or glucokinase catalyzed or catalyze the glucose to glucose 6-phosphate. They transform the glucose into glucose 6-phosphate by the phosphorylation mechanism. So hexokinase is inhibited by the glucose 6-phosphate. This enzyme prevents the accumulation of the glucose 6-phosphate due to the product inhibition. The enzyme, again I am going to tell you, the enzyme hexokinase or glucokinase makes the product glucose 6-phosphate from the glucose. So the glucose 6-phosphate itself inhibits the enzyme hexokinase. That means the more glucose 6-phosphate it produces, it itself inhibits the hexokinase. This type of inhibition is known as the product inhibition. The more product is available, the less enzyme is needed. I mean, if the glucose 6-phosphate is more in amount, then why the hexokinase would be needed? So the glucose 6-phosphate will inhibit the hexokinase or glucokinase. The glucokinase, which is specifically phosphorylated glucose, is an inducible enzyme. The substrate glucose goes through the involvement of the insulin, which induces the glucokinase. This you have to know. So another we are going to talk about is phosphofructokinase. The phosphofructokinase, I have talked about the glucokinase. Let us talk about the phosphofructokinase. The phosphofructokinase is the most important regulatory enzyme in the glycolysis. This enzyme catalyzes the rate-limited committed step. I want you to know that the conversion of the glucose 6-phosphate, which is brought by the phosphofructokinase to fructose 1,6 bisphosphate, is catalyzed by the phosphofructokinase, and this is the rate limiting enzyme. This is the rate limiting enzyme. So the phosphofructokinase is an allosteric enzyme. The phosphofructokinase is regulated by the allosteric effectors. That means the ATP, citrate and low pH. The acidic medium, low pH means acidic medium, are the most important allosteric inhibitor. That means ATP, citrate and more hydrogen ions will inhibit the enzyme phosphofructokinase. That means in the presence of the ATP, in the presence of the citrate and in the presence of the hydrogen ion, the conversion of the fructose 6-phosphate to fructose 1,6 bisphosphate would be low because of the low production of the phosphofructokinase or low availability of phosphofructokinase. So ATP, citrate or the low pH or hydrogen ion will inhibit the glycolysis mechanism because the fructose 1,6 bisphosphate will be low. Side by side, I want you to know that the allosteroic activators that are AMP, ADP, fructose 2,6 bisphosphate are the allosteroic activators. They induces the enzyme phosphofructokinase. That means the conversion of the fructose 6-phosphate to fructose 1,6 bisphosphate will be high. That means the glycolysis will be high. So again I will tell you the ATP, citrate and the hydrogen ion are the inhibitors of the phosphofructokinase, whereas AMP, ADP, fructose 2,6 bisphosphate are the activators of the phosphofructokinase. This way this step is regulated. Now I want you to know that the role of the fructose 2,6 bisphosphate in the glycolysis or regulation by the fructose 2,6 bisphosphate is significant in the glycolysis. It is the most important substrate. Fructose 2,6 bisphosphate is the most important substrate that regulate the glycolysis. I want you to know this reaction. The fructose 6-phosphate is the central enzyme. From here there could be the gluconeogenesis. Fructose 6-phosphate is converted to fructose by phosphofructokinase 1 and it will lead to glycolysis. And also you have to know that fructose 2,6 bisphosphate is considered to be the most important regulatory factor. Also it is the activator for controlling the phosphofructokinase. This I want you to know that. So from the fructose 6-phosphate, phosphofructokinase 2, the enzyme phosphofructokinase 2 again I am going to tell you is that fructose 6-phosphate upon the action of the phosphofructokinase 2 is converted to fructose 2,6 bisphosphate. And this fructose 2,6 bisphosphate activates the phosphofructokinase 1. So fructose 2,6 bisphosphate will increase the activity of the enzyme phosphofructokinase 1. So there will be more glycolysis if there is fructose 2,6 bisphosphate. So and this happened in the fed state. So in the fasting state, what happened? The fructose 2,6 bisphosphatase will be active and fructose 2,6 bisphosphate will be converted to fructose 6-phosphate and which may lead to gluconeogenesis. What happens? We have to know two states. One fasting state, another is well fed state. In the fasting state, what happens? There will be the increased production of the glucagon. The increased production of the glucagon will lead to increased cyclic AMP. You have to know that the cyclic AMP are the second messenger for the certain hormone. So the activity of the phosphofructokinase and fructose 2,6 bisphosphate is controlled by the covalent modification, which in turn is regulated by the cyclic AMP. Again I am going to tell you cyclic AMP is the second messenger for the certain hormones. The cyclic AMP brings about the dephosphorylation of the bifunctional enzyme, resulting in the inactivation of the active site responsible for the synthesis of fructose 2,6 bisphosphate, but activation of the active site responsible for the hydrolysis of fructose 2,6 bisphosphate. So what happened in the fasting stage? There will be the production of the glucagon, more production of the glucagon, which will lead to the increased cyclic AMP. This increased cyclic AMP will lead to increased protein kinase A. This protein kinase A will increase fructose 2,6 bisphosphatase enzyme and decreased amount of phosphofructokinase 2 enzyme. So if there is increased number of fructose 2,6 bisphosphatase, then there will be the conversion of fructose 2,6 bisphosphate to fructose 6 phosphate, and there will be the more gluconeogenesis and less glycolysis in the fasting stage. Whereas in the fed stage, there will be the more glycolysis and less gluconeogenesis. How? In the fed stage, there will be the production of the insulin. The insulin will decrease the cyclic AMP. The cyclic AMP, upon decrease of cyclic AMP, there will be the decrease of protein kinase A. Upon decrease of protein kinase A, there will be the decreased amount of fructose 2,6 bisphosphate and increased amount of phosphofructokinase 2. So what happens? If there is increased amount of phosphofructokinase 2, then there will be the more conversion of fructose 6 phosphate to fructose 2,6 bisphosphatase. And I have told you, if there is more amount of fructose 2,6 bisphosphate, then there will be the, again there I will tell you, there will be the enhancement of the phosphofructokinase 1. And if there is enhancement of this enzyme phosphofructokinase 1, then it will lead to the more amount of glycolysis in the well fed stage. This I want you to know in detail. So mainly these three enzymes regulate the glycolysis. Also the pyruvate kinase. The pyruvate kinase also regulate the glycolysis. This enzyme is inhibited by the ATP and activated by the fructose 1,6 bisphosphate. The pyruvate kinase is active. So pyruvate kinase A is active enzyme and the pyruvate kinase B is inactive enzyme. So pyruvate kinase is active in dephosphorylated stage, whereas the pyruvate kinase is inactive in the phosphorylated stage. So inactivation of the pyruvate kinase by the phosphorylation is brought about by the cyclic AMP dependent protein kinase. So the hormone glucagon inhibits the hepatic glycolysis by this mechanism. So I want you to know that here is protein kinase A, the active enzyme, and protein kinase B, inactive enzyme. So glucagon will increase amount of cyclic AMP, which in turn cyclic AMP will enhance the activity of protein kinase. So upon the enhancement of the activity of protein kinase, the enzyme protein kinase will be phosphorylated. Upon the phosphorylation of the enzyme, this enzyme will become inactive. So if there is the inactivation of the protein kinase A, then there will be the less fructose 2,6 bisphosphate and increased amount of phosphofructokinase 1. So which will lead to more glycolysis and less gluconeogenesis. But you have to know that glucagon is the inhibition. The hormone glucagon is the inhibition of the hormone glucagon inhibits the hepatoglycolysis by this mechanism, by increasing the amount of cyclic AMP. So this you should know very well. So this much for today. This much for this video. I hope you understood the regulation of the glycolysis. Thank you.